All right. Good morning, boys and girls. This is Mr. Chang here, and I'm reaching out from my home to deliver a lesson on trig ratios for angles greater than 90. So let's have a look at this recording and let's go through it. All right. So the first thing I want to talk about is the little details here. So what you want to see here is we're talking about basically doing SOHCAHTOA, but like you don't actually have a triangle to start with, because if you look at what I've got here, I've got a angle that actually goes. Here's the normal angle that we know. It goes from here to here. This is what we call angle theta, or what we call a normal triangle that we build. You can see a right angle triangle, and then you can calculate the angles. If I give you, for instance, a side and another side, you can find that angle. Or if I give you an angle and a side, you can find the other side, right? But after anything that goes beyond this will create an angle that's bigger than 90 degrees. Like if you take this arm right here, which we call, these are the initial arm and the terminal arm. You take the terminal arm and you wind it all the way around. You can go a full, almost 360 degrees. I mean, 360 degrees, you wouldn't have an angle anymore, but anything up to, you would get a very large angle, right? So that actually introduces now our primary angle, okay, which is this winding angle. If we wind counterclockwise, this angle is our primary angle. Okay, what we are trying to refer to now, though, is this relative acute angle. And let me get off of this here. Okay, and this relative acute angle actually works in a different manner. If I can get off of the pen, that'd be even better. Maybe. Is drawing. Okay, beautiful. So that's what we call the reference angle. And so if you look at this little diagram over here, you could see that you've extended the principal angle, or the primary angle, principal angle, past the 90 degrees, and you have what we call now an obtuse angle created, right? It's larger than 90 degrees. And in fact, it could go all the way into quadrant 3 and quadrant 4 if you keep on winding this around. But here we have one that's in quadrant 2, and you can see the terminal arm here stops in quadrant 2. You end up with a pretty large angle. I would guess this to be over 90 degrees, maybe 135 degrees, right? Looks about 45 degrees here, so 90 plus 45 is about 135 degrees. But this related acute angle is the angle that we're interested in about. This related acute angle is the angle that we will now form a new triangle with. And this new triangle will always be based off of the x-axis, okay? The closest x-axis from your terminal arm. So if I was to get to the closest x-axis, we could just make a bow tie kind of idea and just extend all the way down. Okay, so if you take this extended all the way down, we have a new triangle. Okay, and this is the related acute angle, RAA, or sometimes we call it the reference angle. And here it says the acute angle between the terminal arm of an angle in standard position and the closest x-axis when the terminal arm lies in quadrant 2, 3, or 4. And the reference angle helps us determine the exact trig ratios when we are given obtuse angles. Okay, all right. I mean, I already worked this out last night. I was going to go through it with you guys today in person, but I'm sick, so can't. All right, so here we got some practice questions. It says find the reference angle for each of the following principal angles, right? And you can see the angle 250 degrees. So we start from our what we call the initial arm, okay? And we're going to wind our terminal arm. So the initial arm is always on the 0 line right here. And imagine winding a clock backwards in time, right? We're going to take the minute hand and wind it until we get to about 250 degrees. Now, how do I know this is 250? I could say this is like, 0, and this is 90, and this is 180. This will be 270, so we're just about 20 degrees short of it. I mean, halfway through is 45, so I'm a little bit past the half, and I'll get to here, and I'll just kind of make an eyeball mark of about 250 degrees. And so if I take this full principal angle of 250 degrees, I can say my related acute angle is from my terminal arm drawn straight to the x-axis. This distance here is the distance between 250 degrees and 180. This would be 70 degrees, and this is our beta symbol. It looks like the capital letter B, but the stem of the B comes down a little bit more. It's the other angle, the one that we're concerned about. Okay, so that's the reference angle drawn in right there. Okay, against the principal angle of 250 degrees that I mark on the tip here. So if we do the same thing over here, 120 degrees, that 120, you could label that right here, and then the related angle there is 60 degrees right there. Okay, I kind of drew it over here to illustrate that this is 120 because it's 90 plus a 30. I wrote 120 here. The timing is a little weird. So you guys practice on these two and try to create it as well. Next lesson here, next little bit, part 2. There's actually 3 parts today. We got to talk now about evaluating trig ratios for any angle. So how do we calculate the trig ratios, right? See, it says here, for any point, a point xy in the Cartesian plane, the trig ratios for angles in standard position can be expressed in the terms of x, y, and r. And this is how you can do it. You can see, like, if we got the principal and then the terminal arm resting within the first quadrant here, we've created essentially the parts of a triangle here, right? And this 3 sides are actually measured out as the y distance up, right? Y distance for this side right here. This would be the x distance, right? And of course, the length of the arm is r. We can think of this as radius, right? And the length of the r is always considered as a positive. Okay, you always consider this as positive. So the sine ratio to this angle is opposite over hypotenuse. So we'll say y over r, right? The cos theta is adjacent over hypotenuse, so that's x over r. And tan theta is y over x, because that's opposite over adjacent. So then we get into the cast rule. And the cast rule says, all right, so you tell me that if I got the terminal arm here and I create the related angle, right, that B symbol, right, I actually end up with a new triangle on these various quadrants. So with this new triangle, I can work out the sine, cos, and tan ratios, okay? And I could actually see that if I create the sine, cos, and tan ratios, they actually have very interesting characteristics. And that's what we call the cast rule. Okay, it's just as a summary. But if you look over here, what this is saying is starting from quadrant 4, CAST, okay, or some people call it ASTC from quadrant 1. From quadrant 1, you're labeling CAST every time, right? But in quadrant 1, all the trig ratios will work out to be positives here. Positive angle, positives, yeah. Here, all the trig ratios will work out to be negative, except for sine. And that's why there's an S here. The sine ratio works out to be positive. Here, all of them work out to be negative except for tan, and here all of them work out to be negative except for cosine. Okay, and this is something that's really important to memorize because it allows you to have a shortcut to be able to build your angles greater than 90 degrees and calculate the related acute angle and so forth, or the reference angle. And that's what this part says here. So here we say, okay, find the exact value of each of the following, and it says sine of 45 is equal to sine of 45. What is it, right? So if you think about 45 degrees, starting from the initial arm, creating the terminal arm, we're going to make 45 degrees, and that is my reference angle, but you can also write theta because we're in quadrant 1. Our primary angle and our reference angle are the same, right? In this case. And because we're in quadrant 1. And if we look at it here, 45 degrees is right there. That's 45 degrees. 45 degrees labeled there. And if you think about it, that's a special triangle. right? And the special triangle with the 45 degrees here also has a 45 degrees here, and the side measures 1, 1, and root 2. So we can actually calculate that as a ratio. In comparison, if we look for the opposite and the hypotenuse, which is what sine is, the opposite is 1 length, right? And the hypotenuse is root 2, so 1 over root 2. Of course, we can't write it like that. We have to write it as root 2 over 2 because we have to get rid of the radical on the bottom. What about sine of 210? If you look over here, if I take 210, what I do is I go 0, 90, 180, let me lower this a little bit, 0, 90, 180, and then 210 would obviously be in the third quadrant. That's all the way to 270, so it's somewhere in between here. And if I work out the math, that actually is about 30 degrees. If this is 210, I go 180 plus 30 more degrees gets me 210. So my related angle here is 30. And lo and behold, 30 is also a special triangle. So you label out your special triangle. This is the 1 side, this is the root 2, this is the root 3 side, and this is the 2 side because the 2 actually is longer than root 3. We all measured, remember, root 3 is only 1.44 or 1.14 or something like that. 1.414, that's it. So once we got this labeled out, what you need to understand is that the sine ratio is negative in this quadrant. Okay, and you might think of this as like some hard and fast rule. Why is it negative in this quadrant? It's because, remember, what we're doing is we're trying to take the measures of opposite over hypotenuse, right? So, you can actually calculate it and go, oh, that's sine of 30, and then actually work it out. And then the opposite is actually, let me just fold this down. The opposite is actually a distance of -1, right? And the hypotenuse is 2. Right. So instead, what we do is we just build the related angle, and from here we just write it as, look, I already know it's going to be negative because only tan is positive in this quadrant. So that's why I wrote negative sine 30 with my reference angle there. Okay, and that actually works out to be 1/2. Okay. 1 over 2. And we know it's negative because 210 puts us into a negative situation over there in the third quadrant. Then you guys practice the one for cosine and the one for tangent and work it out, and you'll be able to get these answers, right? And so forth. Make sure you can do that. Then we can switch it up and say, okay, I'll do one example here. It says for each point lies on the terminal arm of angle theta in standard position. Determine each of the primary trig ratios for angle theta. All right, so use the wrong symbol there. All right, that's the B. So if we're looking at 5, -12, I would have to draw that in. 5, -12 actually works out to be right here. All right, 5, -12. And, +5 on the x-axis, -12 on the y-axis. Yeah, we're down there. So you go ahead and label the point, and then you create your terminal arm from your origin all the way to your point, 5, -12. And then you just extend it to the x-axis so you could create, again, your right triangle. Always extend up to the x-axis. Never extend to the y-axis. That's not right, okay? So after we've done this situation, we've gone ahead and labeled it. I know it's 5, -12, so that's 5 on the x-axis. There's my side length. -12 is my y length, right? And then if I work out what the r is, I'm going to have to do this business here with the Pythagorean theorem written underneath, and I figure out that r is positive or -13. But remember, we said that here the hypotenuse is always going to be a positive, so I'm going to write the positive 13 there. Now that I have all 3 sides measured out, I got to figure out determine each of the primary trig ratios. So okay, I got to do sine, cos, and tan. And you can just work it out from here, right? I could tell you only the cos is going to be positive, okay? Because cos is going to be, it's written here in the cast rule, right? Only cos is positive here. That means sine and tan will be negative. Okay, good. And here I've just gone ahead and I said, look, sine of theta is equal to, and you could calculate theta, you could write it in here. Actually, no, we don't have the calculation for it. You can calculate it later by doing sine inverse on the -12 over 13. But you write sine inverse is equal to opposite over hypotenuse, which is -12 over 13. And that's that. Cos theta is adjacent over hypotenuse, so that's 5 over 13. And cos is positive, right? And then tan is opposite over adjacent. That's negative 12 over 5. And so that's also going to be a negative. All right, and you guys work out the other ones. Lastly, we got to talk about the unit circle. And the unit circle is a really handy way of looking at it because it's essentially the same as what we were doing on the other side with the previous example, but we are now declaring that the radius is just going to be 1. And if we declare it as a radius of 1, then things actually change very interestingly. Have a look. The unit circle, a circle with a radius of 1 unit, is very useful since the x and y coordinates of where the terminal intersects it tell us the sine or cosine and sine ratios respectively. Because if you look at it here, for any point pxy in the Cartesian plane that intersects the unit circle, the trig ratios for angles can be expressed in terms of x, y, and r. So sine theta is equal to y over r, right? It's equal to opposite over hypotenuse, right? But that's y over 1. And then, so you could just say sine theta in a unit circle is just y. And cos theta is, again, this is adjacent over the hypotenuse, but the hypotenuse is just going to be 1 all the time. So it's x over 1, or just x. And then tan theta will be y over x, the y value divided by the x value. That's the same as the previous example. Okay, but now these are shortcuts. So the y value is always a sine theta, right? Is always a sine ratio, and the x value is cos theta. You check out that link, and there's like a unit circle you can play around and spin around and see these measurements changing. Here's the first example. I mean, here's both if you want to see them. But let's talk about the first example. It says sine of 270. We got to figure that out. Well, 270, we know this if we label this out. This is 9. Sorry. Oh my gosh. This is 0, and this is 90, and this is 180 degrees, right? And that's 270 on the bottom. So we had to figure out sine of it. Remember, as a measure on the unit circle, everything is just 1, right? So it's 1. If I labeled out these distances, this would be 1, 0 right here on the unit circle, right? And this would be 0, 1. This will be here, negative 1, comma 0. And here this would be 0, negative 1 on the 270 degrees. So if you were to think about it, remember, cos at 270 is the x value. Cos is x, right? So it's 0. But sine is sine of 270, which is negative 1. So we're just going to write negative 1, right? Or you could work it out, and that's y over 1, and the y value is negative 1. So negative 1 over 1, which is negative 1. All right. This last bit is, I said it was only 3 parts, but obviously I lied. There's a 4th part here on the negative and coterminal angles, okay? And boys and girls, I really wanted to do this in person and work with you on this stuff, but yeah, again, sometimes the breaks just don't work out. So a negative or a coterminal angle is really just it's just another way of finding your primary angle. Instead of winding around clockwise, we wind it around. Instead of winding it around counterclockwise, we wind it around clockwise. All right. So coterminal angles are angles in the same in standard position that have the same terminal arm. So starting at 30 degrees and rotating 360 degrees counterclockwise will bring you back to the same terminal arm, right? And so if you look at these two examples, 30 and 330 plus another 360, will wind it another 360 degrees, put you in the same spot, right? These are coterminal arms. In fact, if I repeated it a couple more times, add another 360, right? Add another 360, you get these measurements, 30, 390, 750, and 1,110 are coterminal arms. Yes, but what about negative? So negative is when we go clockwise, right? Like see this gray arrow, right? So you can find an equivalent coterminal positive angle by adding 360 degrees to the negative angle, okay? No, that's going to be very important. So for instance, if I give you a negative angle of negative 210, basically you go, okay, fine, 90, negative 180, and this will be negative 210 right there. right? And if you wanted to find an equivalent coterminal positive angle, we just add 360 degrees to this. So 360 degrees added to the negative 210 will give you 150 degrees as your other angle, okay? So it actually turns out to be that negative 210 and 150 degrees are the same terminal arm. So example 5, find 3 coterminal arms to 60. So you can see I'm just adding 360 or 2 of these 360s or 3 of these 60s, and I get all these measures here. Last thing I'm going to talk about, I think, is find the exact value of each of the following over here. So you can see sine of negative 45. I'll let you see the both examples, but here's sine of negative 45, and it says sine of negative 45, that's negative 45 degrees going down. So we go 45 degrees down, right? And this is clockwise now because it's a negative angle, and we'll put ourselves over here. We got a related acute angle of 45 degrees that's built within the triangle that's extended up to the x-axis. I mean, that is a special triangle, and we label it 1, 1, root 2, and we could take in the measurements, but we also know that only cosine is positive down here, so we know it's going to be negative. That's why I wrote negative sine of 45, because I know it's going to be negative, right? And that's that. Just had to convert the radical to a non-radical base, right? Okay, so do the practice. I think I'm going to upload the worksheet as well onto our class site, so have a look at these things and give them a shot. Okay, hopefully you guys are able to learn this stuff and do well with this. I'm really rooting for you guys. I know it's a complicated lesson, so you know, try the practice and work through these stuff. Work with your neighbors and so forth. Okay, have yourselves a great day, and I'll see you guys soon. Okay, hopefully. Bye.